Then let us start. Let me start my presentation. Today, I would like to talk about the very famous paper about the tomography, seismic tomography, the titled Broad Plumes Rooted at the Base of the Earth's Mantle Beneath Major Hotspot by Scott French and Barbara Romanowicz, appeared at Nature 2015. So let me talk about its introduction. Hotspot volcanoes are considered to the surface expression of narrow plumes. This idea was first presented by Morgan in 1971, as I explain later. And they should be originated in the boundary layer in the deep mantle. But then a question is, which thermal boundary layer hotspot originating in? One idea is core mantle boundary, CMB, because hotspots are fixed relative to the global mantle circulation. Therefore, geophysicists consider hot spots are originated in the deepest part of the mantle. And as I also explained later, the locations of the hotspots are correlated to the large low-velocity provinces, LLSVP, which is present at the base of the mantle. And geodynamic modeling also suggests a preferential occurrence of the hotspots above outer low-velocity zones. Some studies claimed the hotspot melting is caused by the shallow convecting processes. They considered this idea because of the morphology of the hotspot seems controlled by stresses and cracks in the lithosphere. However, we do not consider this possibility in the current argument. Then let me talk about several backgrounds to understand this paper. First is the hotspots. As I told you, the hotspots are hotspots are volcanic activity not related to the subduction zones. This is a map of the locations of the hotspot. And the hotspots appearing today's talk is Yellowstone in the North America, or Guadalupe, also North America, Hawaii, Galapagos, Easter, Pitcairn, Marquesas, Tahiti, Samoa, McDonald, and Louisville in the Pacific Ocean, and Balleny in the Atlantic Ocean, Comoros, Afar, St. Helena, Ascension, Cape Verde, Canary, Azores in around Africa, and Iceland and Jan Mayen in the North Atlantic. This map is from a famous paper by Morgan, 1971. The thick arrows shows the direction of the volcanic chains of the hotspots, and small thin arrows denote or express the direction of the plate motion. You can see this is a Hawaiian chain, and this is Liuview chain, or this is a this is a Hawaiian Emperor chain, this is a Tuamotu chain, and this is a Australia Gilbert Marshall Island chain. The direction of the chains of the hotspots are similar with each other within the Pacific plate. And that direction motion is consistent to the motion of the plate. These are also the case in the other hotspot in the other plates. Morgan argued this is evidence that hotspots are fixed in the deep mantle. Next background is LLSVP. LLSVP is the structure of the lowermost mantle characterized by a low shear velocity. This is a map of the shear wave anomaly just above the core mantle boundary. Red part have a low shear velocity, and blue part have high shear velocity. You can see there are two low velocity anomalies. One is under South Pacific, and this province is referred to as Pacific LLSVP. The other is from Indian Ocean to West Africa and North Atlantic. This is referred to as African LLSVP. As I already mentioned, the velocity of LLSVP is minus 2% lower than the average mantle. Therefore, these regions are primarily considered high temperature. LLSVP covers 30% of the core mantle boundary, and this is a volume three-dimensional map of the low velocity anomaly, and this volume occupies 8 volume% of the whole mantle. This diagram is from McNamara, Tectonophysics 2019. This is a very good review paper about LLSVP. The presence of LLSVP is very robust. It is very challenging to analyze the velocity structure on the core mantle boundary because it is quite deep. This is a boat map of the 5 tomographic study of the whole mantle. Megnin and Romanowicz 2000, Hauser et al. 2008, Kustovsky 2008, Simons 2010, and Ritzema 2011. Red color shows all of these 5 studies indicate low velocity region in this, and blue color shows none of these studies indicate the low velocity in this region. You can see the red part and blue parts are almost exclusively present, and for example, yellow part or cyan part, half of the study indicate and The other half do not indicate. Such regions are quite narrow. Therefore, presence of LLSVP are considered very robust. It is a robust feature of the lowermost mantle. In contrast to the shear wave velocity shown in the previous slide, the P wave anomaly is quite ambiguous. These are 4 studies of both P wave and S wave anomaly. These maps shows the P wave, which is given by green color, and S wave shown by orange color anomalies, low velocity anomalies by 4 studies. As I already mentioned, the locality of the low shear velocity anomaly is quite consistent with each other. And however, low P wave anomaly is quite inconsistent among these 4 studies, and also the consistency between P wave anomaly and S wave anomalies are quite inconsistent within one study. Therefore, low P wave velocity anomaly is not robust. Or we can say P wave anomalies should be very weak. This fact is also shown that this contour of the S wave anomaly and P wave anomaly. For example, this one is this contour of P wave S wave anomaly is minus 0.5%, but P wave minus 0.2%. So intensity of the P wave anomaly is half or less than half of the S wave anomaly. S wave, the structure of LLSVP is sharp or not sharp is another question. And this map shows the velocity gradient over shear wave velocity. Dark part shows a steep gradient in a horizontal direction, and yellow curve denote the contour of a minus 27% anomaly. You can see the minus 0.27% contour agree very well with the steepest velocity gradient part. Therefore, structure of LLSVP is rather sharp. This suggests that the LLSVP may be a compositional origin. Low velocity suggests it's a thermal origin, but if thermal origin, the structure should be very smeared. But such a rather steep structure suggests the LLSVP also have a compositional anomaly. Let us focus on the high velocity part. This blue part, this is also a vote map of the several tomographic studies. And the blue part indicates the high velocity part voted by many tomographic studies. The blue part are located under circum-Pacific regions and also Central Asia. as you know, the Circum-Pacific regions are present subduction zone, and Central Asia is under the ancient subduction zone referred to as Tethys. Therefore, many geophysicists consider the high velocity part is graveyard of the subducted slabs. Subducted slabs reached to the core mantle boundary, and it's accumulated in this part. This is a scenario. Next, let me talk about the spatial relations between hotspots and LLSVP. This red part is again the LLSVP, and hotspots are located not very center or inside of the LLSVP, but the outside or margin of the LLSVP with the high velocity regions. There are exceptions. For example, North American hotspots are not located on the LLSVP. And this hotspot, Tahiti hotspot, looks located inside of the LLSVP. But as I show you later, if we see the more detailed structure of LLSVP, this is not inside. So the next is the background of the regarding the ultra-low velocity zone. Ultra-low velocity zone, ULVZ, is tiny patches on the core mantle boundary with a drastic velocity reductions. These are thin red part are LLSVP, but these are thick red part is ultra-low velocity zones. This is a representative velocity structure, proposed velocity structure of the LLSVP. This is P wave, this is S wave. The S wave anomaly is minus 30%, and P wave anomaly is minus 10%. And thickness is 10 to 40 kilometer, very thin, and the spatial dimension is an order of 100 kilometer, 100 or 500 or something like this. So how did the seismologist detect the ultra-low velocity zone? The pioneering work was given by Helmberg et al. 1998. They used so-called SKPTS phases of the seismic wave. This is a cross schematic drawing of the Earth, and these curves shows the ray path of the seismic wave. And this one is S wave propagating in the core, in the mantle, converted to P wave in the outer core, and converted to the S wave in the on the core mantle boundary again, and propagate in the mantle, and observed by observatory here. This phase is referred to as a SKS. K represents a compressional wave in the outer core. SKPDS is a bit complicated, but first propagate in the mantle as S-wave, converted to P-wave on the core mantle boundary, referred to as K, and reaches to the core mantle boundary the other side, and converted to P-wave, and this P-wave go diffracted and go on the core mantle boundary of the low velocity zone, and at the end of the low velocity zone, it is diffracted and converted to S wave and propagated to the observatory. The ray paths of these two waves are similar. As a result, the SKPDS wave appears post-cursor, appears a bit later than SKS wave. So if this part have a very low velocity, the time difference becomes large. Hellenberger et al. Observed the SKS and this later phase in the European stations and American stations. They also use South American earthquakes to detect the ultra low velocity zone beneath the Iceland. So, and the seismogram go through under the Iceland shows this post-cursors. KEV, station KEV, and station KRK, the seismic waves from the South America to these stations go through the core mantle boundary beneath the Iceland. It has a very clear post-cursor. So they analyze this post-cursor more in more detail, and conducted simulation about the low velocity structure under beneath the Iceland. And their simulation implied that there is a ultra low velocity zone below Iceland, which seems 250 kilometer wide, 40 kilometer thick, and P velocity reduction is minus 10%, and S wave reduction is minus 20%. Next study is a Kotar and Romanowicz 2012. They observed an ultra low velocity zone below Hawaii, and they used S-diff wave phase. S-diff phase is this is also a schematic cross section of the Earth, and the earthquake occur here, and it propagate and go just above the core mantle boundary and received by this observatory. And if ultra low velocity zone exists, there is a delay of the seismic waves. This is the relations between earthquake occurred in the Indonesia and many seismic stations in the North America. and these are a bounce point. So they observed this is a main S wave, and this is a postcard. From these later signal, they suggested there is a low velocity zone below Hawaii hotspot. Because the data is limited, therefore there is a trade-off, but they suggested the horizontal dimension of our outer low velocity zone is 900 kilometers, and the S-wave reduction should be minus 20%. But there is trade-off. If the radius is very small, then velocity reduction can be minus 30%. If the radius is large, this is diameter, this is radius. And if radius is close to 600 meter, in the radius 1200 kilometers, then velocity reduction is only 15%. And the more robust study is made by Thorne et al. 2013. They observed a outer low velocity zone with the same method with a Hellenberger et al. 1998. They observed the post-cursor of the SKS, which is interpreted as a SPDKS. In this case, ultra low velocity zone is located in the not the source side, not the observatory side, which was the case in the Hellenberger's study. But in this case, in Thorne's study, they interpret it is located in the source side, earthquake side. Anyway, they observed the ultra low velocity zone from many directions. And they suggested there is a whole of the Pacific LLSVP. This part is not so low velocity, but a medium velocity. And there are couple of several outer low velocity zones in this whole of the LLSVP. And the largest one may be the 250 times 800 kilometer horizontally and 10 to 15 kilometer vertical. And P wave reduction is minus 15%, and S wave reduction seems minus 45%. Then, next is about the plume dynamics. The understanding of the plume dynamics was started by the Campbell Griffiths 1990. They conducted analog experiment of the mantle plume using the organic material, and this dark part is analog of the mantle plume. They suggested if mantle plume is thermal plume, it has a very large head and very thin hot tail, and the diameter of hot tail should be less than 200 kilometers. They also suggested mantle plumes should be the lower mantle origin. So this is the first stage of our understanding about the plume dynamics. However, next, Farnetani et al. Farnetani 1997 conducted numerical simulation of the mantle plume, and they also consider compositional anomaly as well as temperature anomaly. And they assumed the base layer of the mantle have some dense chemical heterogeneity with a higher density. And they examined the shape of the plume, structure of the plumes. This is upper one shows the mantle plume without chemical heterogeneity. And the lower one shows the density, chemical heterogeneity, mantle plume with the chemical heterogeneity at the base with a 5% excess density. These contrasts indicate the temperature intensity of the temperature anomaly. You can see if the composition anomaly does not exist, the contour is denser. Therefore, temperature thermal anomaly becomes stronger. If the density contrast bottom layer have a higher density, the temperature anomaly of the plume is small. And also and this is such relation. Vertical axis shows the excess temperature of the head part, and the horizontal axis shows the chemical density, excess density by chemical heterogeneity in percent. So this is a temperature anomaly on the bottom, and with increasing the chemical heterogeneity, the plume head temperature decreases. So he argued chemically denser layer at the base is essential. Next, Kumagae et al. 2008 conducted analog experiment using some organic compounds. They include the compositional heterogeneity. Green part represents the ambient mantle, and orange part is a chemically heterogeneous part. And this thin part may indicate isotherm. And they heat this analog structure from the bottom. They introduced a buoyancy parameter, which is the ratio of the density contrast due to the chemical heterogeneity over density times thermal expansivity and temperature anomaly. The denominator, numerator, represents the chemical buoyancy, and denominator indicates the thermal buoyancy. Their point is depends on this buoyancy parameters. The plume morphology varies largely. If this compositional effect is small, the mantle plume is very thin, and as depicted by the glyphs and Campbell and glyphs. However, if this buoyancy parameter becomes larger, effect of the chemical buoyancy become larger, plume become thicker, and it has an odd shape. Sometimes some part of the plume falling down and come back to the core mantle boundary, or it stays at the bottom of the lower mantle. They also argued with time, initially the plume go up, but in some stage, temperature effect becomes smaller and plume go back, and it's become asymmetric. Or there is some pulse, such not straight, but thickness varies with depth. Finally, I introduced Lin and Van Keken, 2006. They conducted numerical simulations, but the philosophy is similar to Kumagai 2006. They also introduced the same buoyancy parameter. In this study, the important parameters are density contrast due to chemical heterogeneity, delta rho, and ratio of this delta rho to the thermal expansion effect, buoyancy parameter B, and the thickness of the compositional layer. They categorize thermal plumes into three regimes. So this slide shows the regime 1 called by Lin and Van Keken 2006. In this case, the thickness of the compositional layer is thinner than 80 kilometers, and compositional heterogeneity density, excess density by compositional heterogeneity is less than 40 kilogram per cubic meter. And in this case, the thermal plume is similar to Campbell and Griffiths model. It has a large head and a thin tail. And the regime 2 is a thicker compositional layer or a larger density contrast. In this case, the thermal plume become very thick. This tail part become very thick. And this bottom part undulate significantly. So it is not smooth, but there is several swells. This is again, this is a regime 1. The compositional layer is quite smooth in this case. And in the regime 3, which in this case conditions are between intermediate of a regime 1 and regime 2. In this case, there is some pulsation of the plumes. So the plume, there is another plume head below at the bottom of the plume. So plume occurs not once, but twice or third in this regime. Then in the last part of the background of for this study, I talk about the previous tomographic studies. detection of the mantle plumes are very challenging because the seismic wave must be very long due to large depth. Therefore, it is very difficult to detect thin structure. And because of the low velocity, wave front healing occurs. I don't quite understand what is wave front healing, but in my understanding, if there is a velocity, heterogeneity in the velocity structures, the wave front have such a propagate horizontally, not only the direction of the wave propagation. As a result, there is a multiple head of the wave front, a multiple wave front, which smear the seismic signals. And the third difficulty is the location of the plumes are often in the middle of the oceans, which because of the such locations, seismic networks, the earthquakes density is quite sparse. If we study the subduction zones, there are many earthquakes there, and also there are many countries of developed countries in the subduction zones. As a result, there are dense seismic networks. Nevertheless, there are several studies challenge to the detection of the seismic mantle plumes. One is Chao et al. 2004, one is Monterey 2004, and one is Suezgo et al. 2009. So their questions are where plumes have broad heads and narrow tails, and whether plumes are vertically continuous, and how distinct plumes are from the other low-velocity zones. This slide shows the results of the Chao et al. 2004. These are cross-sections beneath Hawaii islands. These are under Hawaii Island, and this is below Iceland and Jan Mayen in the North Atlantic. This is Tahiti Marquesas and the Cook Islands, Southern Pacific, and this is Afar Lake Victoria and Afar in the East Africa. They depicted the very large low velocity zones below Hawaii and Tahiti. But these plumes are not straight, but horizontally inclined. And they did not detect a clear high low velocity in the lowermost part of the lower mantle below Iceland. But in the case of Iceland, still there is some low temperature, low velocity region. But below Afar or below Lake Victoria, the continuation is even more inclined. Next is Monterey et al. 2004. These studies detect plumes more clearly. So this is below accession hotspot in the Atlantic, and This is the Azores Canary Islands. They detected the mantle plume down to 150 kilometer depth. So in the easter, its low temperature, low velocity region seems continue more, and Hawaii seems continue to 1900 kilometer, and in the case of Samoa or South Pacific spot, it seems continue to the core mountain bound. In this hotspot, Bowie or Eastern, Etna, Eifel, Galapagos, Iceland, and Cocos hotspot, the trace of the low velocity zone is discontinuous to the lower mantle. Finally, Sweatsweater 2009, they studied the velocity structure beneath Pacific super well. Pacific super well is the region where the ocean floor is raised by up to 1,000 kilometers. It is located around here, South Pacific, near the East Pacific rise. There are several hotspots there: Marquesas hotspot, Society Islands, Arago Islands, and McDonald Islands there, and Pitcairn Islands there. And these are cross sections of 600 to 700 kilometer depth, 800 to 900 kilometer depth, 1100 to 1200 kilometer depth, and 1300, 1400 kilometer depth. The low velocity zones exist below the hotspot, and they are separated each other in the shallow zones. But with increasing depth, they merge and become large. So they also, this is a vertical cross section. This shows there is no continuous low velocity zones in the upper mantle and lower mantle. So from their study, the lower mantle and low velocity zones and the upper mantle, lower mantle low velocity zone and upper mantle low velocity zones are disconnected. And below Society Island or McDonald Island, low velocity zones in the upper mantle and lower mantle, but in the it is sorry. No, this is not wrong. Correct. But anyway, there are very strong low velocity zones in the lower mantle, but its a connection with hotspots are unclear. The low velocity seems suddenly appear below 1,000 kilometer depth. Then this is a explanation of the background for the current study. Do you have any questions?